Okay, so welcome back. Last time we were talking about Eudoxus. Uh, Eudoxus is typically considered um, probably the most. So I mean, this is slightly up for debate, but this is Eudoxus is usually considered one of the greatest mathematicians prior to Archimedes. Um, and so he had several notable contributions, both directly to Euclid's Elements in the form of books 5 and book 12, but also in a fact that is also listed in the Elements, but that we've already mentioned, which is this fact about computing the area of a circle. So the thing I was talking about at the end of lecture last time was his theory of proportion. Um, as I mentioned, the reason why this is such a big deal is because for the Greeks, all of these quantities were coming from geometry. And it happened that in these geometric problems, a lot of times you would want to form ratios of objects that um, didn't necessarily make sense if you were thinking naively in terms of ratios as products, right? So I had noticed, or I had mentioned this defining two fractions to be equal if this cross multiplication, right, worked out, if you had equality here. So because Eudoxus planned on using these proportions to these proportions or these ratios to define multiplication, he couldn't use multiplication to define the proportions, and so he was starting from scratch. And to try to make sense of these quantities, as I mentioned, ratios of, say, side lengths, that was fine. Ratios of angles, that was fine. But if you mix those things, right, where now on the right-hand side here, you have AD and BC, and A is, the length of some segment or arc of a circle or something, and D is an angle measurement. It doesn't really make sense to multiply those things. And so if you want to be able to compare ratios without trying to think algebraically how you deal with weird multiplications like this, you got to work from scratch, as Eudoxus did. And what Eudoxus did, as I mentioned last time, ended up being very similar to what would later be done by Dedekind in the late 1800s, which is the construction of the real numbers as we know them in the modern sense. And this process is known as construction of the reals via Dedekind cuts. Okay, and this is essentially what Eudoxus did. So, the rigor wasn't on the same level, but this was basically what Eudoxus was doing, and this allowed the Greeks to deal with these quantities algebraically. So this was the algebraic underpinning for the later parts of Euclid's Elements. This is book 5. Okay. So one of these types of ratios that he was interested in. So here's an example. Imagine that I have. Let me get my tools of construction here, since I'll need them later as well. So one of these quantities was, imagine you have a segment, right, that we'll call AB, and you want to try to divide this segment in such a way, put it here, I'll call this point H, and you want to find this H to be such that the ratio of the entire segment to the larger part that you've divided it into here is the same as the ratio of the larger part to the smaller part. So the ratio of the whole to the greater part is the same as the ratio of the greater part to the lesser part. So rewritten, this is saying that the length AH divided by the length HB, right, so AH divided by HB, I want to set this up in such a way that this is the same as the entire length of the segment AB to the larger part AH. Okay. And now, if I set this up in such a way that the quantity that I want to find how long out here I need to go is x, while this is my unit 1, if that is the notation that I use here, what does this mean in modern notation, right? If AH is x and HB is 1, then let's do our modern thing here and think about we would cross multiply and see what is going on here. What would I get? So this ratio tells me that cross multiplying I would have x squared is equal to HB times AB, but HB is 1, so then I would just have AB, the entire length, which is x plus 1, right? So here I would have, x squared is equal to HB, which is 1 times AB. 1 times anything is just the thing itself. But what's the length of AB? It's x plus 1. Or the quadratic equation that looks like this. Okay. What are the roots of this, right? Let's be Babylonians, use the quadratic formula. What are the roots? Well, using the quadratic formula really quickly, this is minus 1 plus or minus. I'm going to take the plus here, so this is minus 1 plus square root of b squared minus 4ac. Well, b squared is minus 1 squared, so that's 1. Minus 4 times a, which is 1, c, which is minus 1. So that's 1 plus 4, or 5. So this is minus 1 plus root 5 over 2. And so we've encountered this before. We encountered this ratio cropping up in one of the measurements involved in looking at cross sections of regular polyhedra. But this is the golden ratio, or sometimes called the golden section. This is the golden ratio. Okay, and this is how it arises out of this proportion defined in this way. Okay. So apart from the theory of proportion, which is extremely important, Eudoxus did a couple of other things. So Eudoxus also showed that the area of a circle is proportional to the square on its diameter. Okay. And he did this by inscribing 2 n-gons. This process that we talked about before. So 2 to the n-gons. Okay. Alright. So by inscribing these 2 to the n-gons and picking a value of n that's large, this was it. Oh, you are right that in the previous one, minus b would be plus 1. So typically this would be plus 1. Why did I write minus 1 there? Did I just screw up, or was I doing something else? So it turns out that x squared is equal to x plus 1, and 1 over x is actually equal to x minus 1. And this pair of numbers that you get, the pair of solutions you get here, are the unique real numbers that satisfy that. Okay. And what that means is that actually x minus 1 is sometimes also called the golden section or the golden ratio, because the decimal expansion is the same. After the 1, the decimal expansion is the same. So this is like 1.618033887 or something. With a -1 there, it's actually the exact same, except it is 0.618338887 or whatever. So anyway, so both this and -1 plus root 5 over 2 are related in this way. So the difference between these is actually just a 1. So think about that for a second, that what happens when you add 1 to this. So anyway, and actually it's this quantity, not this one. It's this quantity, I think, that shows up as the ratio of that cross section of a regular dodecahedron. Yeah. Okay. So this is what Eudoxus also did. This was, one of the celebrated things that he did. Also included in the Elements was this argument. There's one more Athenian mathematician I'll mention before talking kind of generally about Plato and Aristotle, and then going on to composite and straightedge constructions again, which is another student of Plato's, which is Menachmus. So, Menachmus. Okay, student of Plato. So he's a student of Plato, was active around 350 BC. He discovered the conics. Okay, so unfortunately, I do not have a good model of these. What are the conics or conic sections? So basically, if you imagine a double cone system, so a double circular cone, we'll say. Okay. It turns out that a lot of the classical curves that Greeks were interested in can be described as cross sections of this double cone meeting a plane. Okay, what do I mean? Well, if the plane passes through, if it cuts through that apex point where there's double cones meet, that's a point. How do I get a line? A line is when the plane is like perfectly tangent to these double cones like this. That intersection would be a line. Okay, what if my plane cuts through one of the double cones like this? What do I get? These are circular cones. If you think for a second, what is the cross section you get when you cut a circular cone with a plane parallel to its base? You get a circle. All right, that's if it's perfectly parallel to its base. If you take the plane and you come through at an angle, what kind of curve is that? It's an ellipse. Okay. It is a more eccentric circle, right? It is an ellipse. So this is what you get when you cut through like this. What happens when you come through at an angle, but you come through at an extreme enough angle that you actually don't touch the other side of the cone? So you come through at an angle like this. What curve do you get? Let's do it down here since we haven't marked anything. What curve do you get from cutting this double cone system with a plane like this? You get a parabola. Okay, exactly, yeah, a parabola. What curve do you get if you cut this double cone system with a plane like this that intersects both cones in a disjoint way? What do you get? Well, let me draw it like this. So these are taken together. If we draw them in the plane, yeah, as someone said in chat, a hyperbola. Okay, this is a hyperbola. Okay, and so ellipses, hyperbolas, parabolas, these curves were discovered by this student of Plato's. And basically, he used these to double the cube. Okay. Of course, as I've mentioned many times, this would not be acceptable. This was too advanced of machinery to use for those problems, and so this wouldn't solve the problem in a satisfactory way. But this was the use that he came up with for these curves. Now, most of these curves would be developed in antiquity, wouldn't happen later. So later, Apollonius of Perga, so much later, would exhaustively study the conic sections. In a work that would be basically the last great piece of mathematical writing for almost 1,000 years. So by the time of Apollonius, basically from Apollonius to the next great mathematician was a gap of at least 500 to 600 years of essentially nothing new being done. Now, does that mean like conclusively absolutely nothing new was done in that time? No, but there's just no record of it. So basically there was a span of 500 to 600 years after Apollonius where absolutely nothing happened in terms of mathematical understanding. So anyway, but this was the first discovery of these beautiful curves. So, quick aside, Plato and Aristotle, and as I only half joked last time, why Plato is so much better than Aristotle is what I should subtitle this rant. So, neither Plato nor Aristotle had a huge direct influence on math for reasons I mentioned previously. The biggest influence Plato had on math is, as we'll see, the insistence, supposedly, right, this is due to Plato. We don't actually have like a definitive attribution of this fact until almost 600 years later. Pappus of Alexandria was the first to mention that it was Plato that insisted on this. So, it's not definitive, but this is generally agreed upon that Plato was the one who insisted on compass and straight edge constructions for these classical problems. And that's Plato's biggest contribution, other than having some students that did some things individually. Plato himself didn't really do much. Aristotle didn't really do anything as a mathematician. The main influence Aristotle had to do with his philosophy and his disagreements with Plato. Of course, it turns out Aristotle is wrong about everything in a sense. So I don't want to get into a super long discussion about the philosophy of Plato and Aristotle because that would take way too long, way more time than we have. There's plenty of things to discuss here. So then, what's some quick treatment of this that you've no doubt seen in some form, at least a little bit, right? So Plato's, one of the central topics of discussion in Plato is his putting forth this idea of the problem of universals, which he developed his theory of forms to describe. So, the easy, distilled version of this is that the forms exist in the world of the forms. They are perfect, absolute, unchanging. It is easy to think of mathematical concepts as inhabiting this plane. So if we stick just to math, it's actually a much easier sell in a way than if we start talking about the form of, a cup or the form of a chair. Um, so, the sticking to mathematical concepts, it's if I draw a triangle, a circle, a line, whatever, any kind of picture, any kind of image I draw, right? As a mathematician, I understand that the object of study is not what I've drawn. I've drawn a picture, a representation of that object. The actual object I'm studying lives, in form land. Okay, so my drawing of it is just a crude approximation of it, right? My line, any line that I draw, it is not really going to be perfectly straight. Any angle I draw, if I try to draw a right angle, is it going to be perfectly 90 degrees, right? Is it going to be a perfect right angle? Well, maybe, if I zoomed in enough, you could see that, no, not really, right? It's slightly off, right? By like 2/1000ths of a degree or something. So that is, that is to say that we draw representation, we do computations, and as long as we follow the rules of logic, right, we do this computation in our world, but we're computing in the world of the forms. And so we say something that is true in the world of the forms, and so in a sense it's universally true, even if what we have used to show it is crude and not in a sense not as real as the thing in form land. So an example of the strength of this, right? We understand that these perfect triangles that are completely perfect, have perfectly straight sides, they meet at angles that are completely perfect. They exist in the world of the forms. They don't actually exist in reality. Okay. But even though that's the case, we can use those formland triangles, right, or crude representations of them that we draw in the dirt, okay, to approximate, say, the distance of a ship, right, to the shore, right, just based on some simple observations, right? So this understanding that, like, we can compute in the world of the forms, and it actually says something about the real world. You're almost projecting that computation into the real world. This is kind of a very, this is, the mathematical form of Platonism, where you're computing in form land, and then you're projecting your results into reality, and you're actually saying something that's predicting something happening in reality, and like, why does it work out like that, right? Well, Plato would say that it's because, reality is basically a projection, an imperfect, flawed projection of the forms. So anyway, that's kind of, Plato's whole spiel. So, and I've mentioned previously that this is something that is still very much a topic of debate in the philosophy of science, especially when it comes to theoretical physics, and this question of, is our universe literally a mathematical object, or is it an approximation of a mathematical object, right? Or basically, you can describe a space. So there's a type of space in math called a manifold. Do we live on a manifold? Well, the standard model of physics says yes, we live on some sort of manifold that maybe has some singularities. Okay, so we live on some kind of rough manifold or manifold-like object that literally the universe is a mathematical object, not is approximated by it. So, the real universe, like, we literally live on a math object, and this meshes with Plato's, notion that the numbers and the triangles and the lines were somehow more real than, our crude representations of them. So anyway, that's the Platonic view, and that is very much in line with modern theoretical physics. It's very much in line with math, too, because math went in a direction, ultimately, as we'll see near the end of this course, where the abstraction reached a point that required some pretty fundamental rethinking of like how math was done. And at the time, there were some mathematicians that were very much opposed to this. So some of them you could call finitists or intuitionists, I believe they called themselves, or constructionists was another, or yeah, constructionists or constructivists was another name for them. So we'll talk about that much later in the course. But Aristotle kind of fell into this camp where Aristotle didn't believe that any of these infinite quantities really existed in any kind of way. And it's easy to see some hesitancy, right, that you might have whenever, Plato or a mathematician is computing with quantities that are technically infinite, like a line, or even, if we're bringing it to more modern math with calculus, you're using infinitesimals to compute these limits, and we've already seen the issue that limits posed for Greek mathematics and what it meant, to have finite number of steps versus an infinite number of steps. In Zeno's arguments that motion was impossible. So you can see how acolytes of Aristotle might be rightfully concerned with some of these arguments being made, this passing to infinity. But this, it can be uncomfortable, but the issue is if you stay in the finitist worldview, you've really hampered what you can actually accomplish. So there'll be some specific things that I talk about later, but one example is for instance, infinitesimals and a lot of these limiting arguments, that were required to give calculus a rigorous foundation are not, Aristotle would flatly reject them. So in fact, the textbook actually mentions some specific things. So Aristotle's objection to Cantor's Aleph null, so I'll talk about what that is much later at the end of the course. This is the notion of countable versus uncountable and having different degrees of infinity, right? Different sizes of infinity. Aristotle would have very much been opposed to this idea. And this is the example the textbook gives is in metaphysics. He would have rejected infinitesimals. This is in physics. He would reject He did reject infinite sets and infinite magnitudes. So infinite lengths, infinite sets, he flatly rejected, even as they were considered in his day. And so his contention was, well, if you're a mathematician and you're computing with, cardinality. So the set was saying, when it comes to cardinality and the notion of infinite sets, I mean, he didn't even believe in the notion of infinite sets. So the notion of having a set that was not only infinite but was of a different size than some other infinite set would have definitely really, really bothered Aristotle. And I mean, you can't blame Aristotle too much because it bothered a lot of mathematicians at the time anyway. And this was only 120 years ago that Cantor first showed these results. And not every mathematician was super pleased with the implications. So Aristotle is definitely not alone in this. But Aristotle, his premise was basically, okay, look, if you're a mathematician and you're dealing with a line, you can have as much of that infinite line as you need for your computations, okay? But you can't have all of it, right? So to reframe it in the form of Zeno's paradox, it would be that you can take as many steps as you need, but you can't take infinitely many steps, right? Would have basically been Aristotle's take on it. Now, the question, it's actually an essay question in this section, is how might Aristotle respond to Zeno's arguments against motion? But anyway, so Aristotle was definitely a finitist in this way. Now, my my dislike of Aristotle is basically, I'm looking back from now, and it just turns out that basically Plato was right about a lot. And Aristotle was wrong about a lot. um, but there was a time when Aristotle was held in much higher esteem than Plato when it came to the sciences. So, Aristotle was hugely influential during the Islamic Golden Era, which we'll talk about. And so Aristotle was actually much more widely read as as a scientist and someone discussing the philosophy of science, was much more widely read than Plato during that time. But ultimately, as I said, basically all of Aristotle's ideas are wrong in some sense, versus most of Plato's ideas are right or almost right, which is pretty amazing. And of course, I don't want to get into like too much the specifics of that. The main things that I touched on are what I already mentioned, which is it's amazing that Plato's theory of forms can be adapted without too much work from what Plato himself said to basically serve as a nice discussion about the current state of theoretical physics or the math involved, or just general bedazzlement at math being so good at explaining so many things that seemingly some mathematical fact that was developed without regard to anything having applications like in a very specific way, like physically, like applied to the universe, is pretty amazing. So yeah, and I'll talk more about that, especially as we talk more about the direction that geometry headed. But anyway, that's kind of my main rant about Plato and Aristotle. Aristotle had some other things. So he also spoke about this ancient question of what is it that makes, like, is matter composed? Is it like a substance? That is it like a continuum, or is it atoms? So his take on that was basically that you could have atoms arranged into like quanta or forms that you would count, right? So his example of this was like basically like it was like if you had, like, consider wine and bread, right? So if you're talking about like a loaf of bread or a glass of wine versus like loaves and glasses are counted, but bread and wine are measured, right? This is basically, whether you're counting or measuring is a way of formulating this problem of whether you are, whether you think something is made up of atoms, right, versus substance, which has to be measured, right? Atoms can be counted theoretically, and the substance, a continuum, would have to be measured. So anyway, okay, so then the thing I want to focus on is, as I mentioned, Plato's main contribution, which was the insistence on compass and straightedge constructions. So, compass and straightedge constructions. Now, as I mentioned, if we take Plato's insistence as kind of like the rules of the game, right, then what am I allowed to do? So, I'm allowed to use straightedge. Imagine my straightedge has no markings on it. I can use it to take a given segment, right? Say that I have, oh my god, that's terrible. Say I have, let's draw an actual straight segment without me moving this thing. Okay, so say I have a segment AB. All right, I come across this segment. But in order to prove something about it, I need to extend this thing. Okay, I need to extend it to be longer so that I can talk about maybe some intersection this segment would have if it were longer. Well, I can use this straight edge to extend my segment. Okay, I'm allowed to do that. Now, actually, that's all I'm allowed to do with this. Okay, this is used merely as a tool for, making segments longer. Okay, for extending these segments. The other thing I'm allowed is the compass. What can my compass do? And you might say, well, a compass can trace out circles. Yes, it can. And you're allowed to do that. But really what you're doing is you're transferring length. So the compass is the measuring tool, not the straight edge. Okay. And so I have measured this length AB, and I can transfer this length using my compass. So if I have another segment over here, I can compare the lengths of those segments by transferring the length to see how they compare. Okay. Now, you might say, okay, you can use this to trace out circle, but what are you really doing when you do that? Well, you are saying that every point that is on this curve that you're tracing out is exactly this distance from A. A is the center of that circle. I do the same thing from B, of course. Okay. Now what am I going to do? Well, I notice I get 2 points here of intersection. Let's pick this one. Well, what's true about this point? Okay, so what's true about that point is it is this distance, this indicated distance from A. And it's also the same indicated distance because I didn't move my compass at all in drawing these two circles from B. And I can just check directly. Oh yeah, it is. So I found a point that is the same distance to A as it is to B. I'll call this point C. And I will draw these edges in using my straight edge, which I'm allowed to do. And what did I just construct? Well, I can see just directly by comparing these lengths, I've constructed a triangle, all of whose sides are the same length. Okay, so I have constructed an equilateral triangle. I've constructed a regular three-gon using nothing but compass and straight edge in exactly the way that they were supposed to be used. Okay, so this is clearly a construction that can be done with compass and straight edge. Okay, what else can I do? I can bisect an angle. Let's see how to bisect an angle. So let's start out with some angle. There is our angle. How do I bisect an angle? So here's some angle, and I want to bisect it. Let's call my angle ABC. Okay. I take compass. I open it to whatever length I want to. And I go to my angle vertex, B. I sweep my compass through both rays, making up the angle. They intersect at these intersection points. I keep my compass the same length. And I make an arc out here. I switch to the other intersection point, and I do the same thing. Why did I do that? Well, now I found a point. And if I use my straight edge to connect to the point, What did I do? I've bisected the angle. And if you think about what every mark here means, you can work through. Every mark there is a step in a proof. So you could translate this to words. That would be a full, complete mathematical proof of this line that I drew bisecting that angle. Now, these are two of the first things that you do with compass and straightedge. This construction of the equilateral triangle is literally the first thing that Euclid does with compass and straightedge. So this is the first construction in Euclid's Elements. This is literally the first thing that's done. Okay. All right, construction or bisecting the angle is also quick. All right, this is one of the simplest things you can do. Now, seeing this and then asking the question, well, bisecting an angle seemed really, really easy. Right? And of course, if I can bisect an angle, then I could bisect each of these bisected angles, so I could quadsect an angle, right? If I wanted to break it into fourths, okay, that's no problem. In fact, if I wanted to break it into any powers of 2, that's no problem, just by repeatedly bisecting. Okay, but then that makes you think, how can I trisect an angle using these same rules? Right? It seems like it should be something I can do. And it turns out that it's just not. Right? I just can't do it, right? As we've saw, I've already spilled the beans on that. Now, I'm actually going to show why you can. But before I do that, I'm going to list out again the classical problem. So what are the things you can do? Clearly, we can construct an equilateral triangle. We can bisect an angle. We can bisect a segment. Okay, bisecting a segment comes next after this. So I want to bisect AB. It's not as hard as you think. So bisecting a given segment AB is not bad at all. I can construct a parallel, right? If I draw a point not on a line and a line off that line, I can construct a parallel to that line through that point. Okay, these are all things I can do, all right? So then there are some related things that seem like, why shouldn't I be able to do these, right? So the classical problems, as I've listed before. So 1, doubling the cube, the Delian problem. As we've seen, this is i.e. constructing the cubed root of 2. Problem 2, trisecting a given angle. So trisecting a general angle. It is possible to trisect some angles. Okay, so there are angles that I can give you that it is possible to trisect. For instance, a right angle is really easy to trisect. Okay, but doing it for a completely general angle is the question that's wanted. So say an angle of 60 degrees, i.e., right, even doing it for a 60-degree angle. Okay. The next problem is squaring the circle. Okay, i.e., constructing a square equal in area to a given circle. As we'll see, this is basically constructing the square root of pi, right? So i.e. constructing square root of pi. Okay. Now, as we've seen, as I've mentioned many times, there were solutions to these problems, right? In fact, even Hippias, right, was an early solver of 2 of these problems. Hippias used the quadratrix to solve trisection and squaring the circle. Okay, but this was tossed aside by Plato as not being a proper solution. And so when we talk about solving these problems, we talk about doing it with compass and straight edge. Okay. Um, as I said, this seems maybe like you're just needlessly creating strict rules for the sake of it, just, to challenge yourself, whatever. It's kind of like hard mode, right? But it turns out that this really is like conceptually something that occurs when you're talking about these things. There is something going on under the hood that really is showing that, like, once you are understanding enough to resolve these issues and say why you can't do these with compass and straight edge, then you have basically passed like a critical threshold for understanding what it is that's going on here. Okay. And so I'm going to actually explain why we can't do this. But for us to actually understand why we can't do this, first we have to understand what we can do with compass and straight edge. Okay, so I showed some examples of what we can do. So, question, what can we do? And of course, when I say we, I'm talking about what was it that the Greeks realized could be done with compass and straight edge? Well, it turns out that apart from a couple of examples, the Greeks basically did almost all that could be done with compass and straight edge. So, to see how they understood, so answer, quite a lot. And algebraically, what could be done was adding, subtracting, multiplying, dividing, and taking square roots. Okay. So, you could add, you could subtract, you could multiply, you could divide, and you could take square roots. These first four are called the rational operations. You probably see why. Because if I begin with rational quantities, that is quantities that can be written as ratios of whole numbers, if I begin with rational quantities, then adding, subtracting, multiplying, and dividing those, I still have rational quantities. The only time I have to worry about moving to an irrational in that case is when I'm taking square roots. Okay, but it's going to turn out that irrationality is not necessarily what is the problem here. In fact, it's not specifically the problem. For instance, right, you might be tempted to say, well, I mean, constructing cube root of 2, constructing square root of pi, that's clearly going to be bad because these are irrational numbers. Okay, but I could tell you, construct for me a length having, or construct for me a segment that has length square root of 2. Well, that's easy. You just draw unit square, right? In fact, if I had you coming up with lengths for square roots, because we know that algebraically with compass and straight edge you can extract square roots, in fact, if you can construct rational quantities, which it turns out you can do, because you start out with unit length 1, and if you start out with 1 and you're allowed to add, subtract, multiply, and divide, that gives you all the rational numbers. Okay, so you have any rational number you want. Okay, and then you have square roots of rational numbers. Okay, and we'll see how you have that. I'll have to wait till next time to show you how that works. So you have the square roots of rational numbers. Okay, so it being irrational is not the problem. It's different than that. Okay, it's more subtle than that. And so we will see exactly what goes wrong next time. Next time I will show why these are impossible. I won't do the full proof of it because it requires math that came 2,000 years after these problems were stated. And it also requires math that has not been seen by everyone in an undergrad math program. This is stuff that you don't see done until a first course in abstract algebra, like 400 level math course in a typical undergrad program. And it requires something called field extensions. Okay, so this is what is required to adequately explain exactly what it is that's going wrong here. Okay, specifically, it is multiplicativity of the degree of finite field extensions. This is the key that you need, and I'll talk about that next time. So in a way that is approachable for everyone, I'll show exactly what it is that goes wrong here. And then we will move on to Euclid after I've mentioned this. So I think that's that. So I think I've just run out of time. So I will see you all on Friday, where we'll show that these things are impossible. So yeah, pay attention to announcements. I may post a bunch of info from some of these previous chapters too, because I was actually trying to compile a list of nice info here. So yeah. Anyway, take care. I'll see you all on Friday.